Hey everyone, I am going to do my best here to show you how to do this mega FRQ calculator required unit 4 on the applications of derivatives practice quiz. So if you get your calculators ready, we will get at it. This is a fourth degree polynomial. It's positive on the lead coefficient, so we know that its left and right hand behavior is going to both be tending upwards towards positive infinity. It has a closed interval, very important. It's only going from -3 to -4 to +4. So when I go to the calculator, you'll see here that I've got it typed in very carefully. And then when I go to my window, you can zoom 6 it if you want, but what I would typically do is go to your closed interval, type in the negative and positive values there for the minimum, maximum values for x. The scale often is good for 1 in the x's. I just turn it off for the y's because it's very commonly in the hundreds, if not the tens. So you have to guess and check a little bit, which I have done, but you'll get that pretty quickly. And then the graph looks something like this. Okay, so that makes sense. It is not doing anything too unusual. It's located right around the origin, so that all looks really good. And then getting right into the questions, then you can sketch that out, and when we can label that, I'm not going to be able to label it just because of the difficulty of typing and drawing in the computer, but you'll be able to do that on your own quickly. It says find the intervals of increase and decrease. So if you go to the calculator then, and then if you have teed up in advance in your y equals the derivative, I've got it down here in y4, so I can just arrow down and then turn that on at y4. And while I'm there, I find it really useful to have a y equals 0 equation, because to find the intersection, or to find the zeros, it's often easier to find when that intersects with a line drawn at 0. You can also use the second trace, the calculate feature, to find zeros, but this is a little clever shortcut. So going back to the graph then, we see our original and then our derivative. Here is the other line. If you've got a color graphing calculator, that is perhaps a little bit clearer for you, but I do not in this situation. Anyway, we want to know where the increase and decrease intervals are. So that's going to be where the zeros happen in my derivative. So to find a zero, to find any one of these zeros, I can do second and then the trace, and then I'll choose a zero. Sorry, I'll choose intersect to use that y equals 0 feature. And then I just want to make sure I've got the derivative equation in the upper left corner here. It tells me which function I'm graphing. I'm on y1. I want to be on y4, so I down arrow. And actually, I'll choose 0 because I want to know where it's a 0. And then I'll go down to this one. And I can go left or right to get to the closest one. I'm going to start here on the right-hand side, so I'll get closest to that one out there. And then if I select enter again, it'll say guess. Well, I'm not going to guess because I just want the answer, and that is 2.552. 2552. So if I go back to my answer and I find all of those, they're going to look something like this, where I get, there's the 2.552, the other one is 0.087, and the first one is -2263. My decrease is there and my increase is there. I will not read those out, but I've used those A, B, and C points just to make it clear. So you can read that, you can pause and read that. Okay, finding the intervals of concavity and the inflection points is very, very similar, but I'm just going to go to my calculator now and go to y equals, and I'm going to go down and turn on the second derivative right there by turning on that equal sign, hitting select. I've made this thick. Again, if it was color, it wouldn't be quite so cumbersome. It looks very, very hefty there, so we can definitely see that second derivative. In finding the zeros, I also can just find the intersection of that, my fifth y5 equation and the 0. And again, just to save time, I think you understand what we're doing going back to this. I find the intersection points, meaning the zeros of my second derivative, are at -1.515 and +1.267. That means it's concave up wherever that second derivative is above the x-axis. That's from -3 to that -1.515. And then it's also concave up from my 1.267 to the end point there at 4, concave down in between. So those are the inflection points there, because that's the boundaries for my concavity. So then the absolute and relative minimum and maximum function values, those I'm going to use the closed interval method, where I start and end with an endpoint, and then I do those critical values. Those are my A, B, and C values. I've actually plugged them in to the function. So if we pick any one of them, just to illustrate how to do that. So if I'm interested in finding what is the function value at, say, this point C, which is that 2552 value we found, 2.552, I just go back to my graph. And if I want to, just for clarity, I can turn off those two lower functions just so that we don't see them. It gets a bit annoying. You do not have to do this once you see the functions quite clearly, especially if you have a color graphing calculator. So if I go back, there's my function value, and then I want to just do second and sorry, I do not want to do second. I just want to do trace. And when I trace, I can type in any value. I can type in 2, and it'll give me the function value at 2. I want to type in 2.552, if I recall. And when I hit enter, that is the absolute minimum value there, negative 41.374. And there you see it, negative 41.374. So you can find those values, and you'll see, just label carefully what's going on, and you'll have those without much difficulty. The point on the function that is closest to the fixed point, 2, 0. Now this is an optimization. Okay, that's a period there. It should be draw a separate illustration to show how to set up this solution. All right, so I am not able to draw that here on the computer, but if you go back to this graph, what it would be is, out here, this is 2, and we're trying to find the closest straight line point. I'm guessing it's somewhere straight down there to that point right there. There's actually 2 ways to find it. One very clever way would be knowing that that line straight to that floating point would be perpendicular to the tangent at that point. So that's an entirely different way to solve this. We're going to do it as an optimization, which means we simply need to model the distance from this point, 2, 0, to a point down here on the function, and think of it as a little mini distance formula. So you're going to do a little drawing that looks like a little right triangle, and then you're going to write it into an equation, which is what this is going to look like. So if I go like this,